I would like to address in this video the solving of ordinary differential equations with a Dirac delta forcing term on the right hand side. So this would be similar to how there are two ways of pushing a swing. Someone is swinging and you can provide a periodic forcing, or someone is swinging in a swing and you just kick the swing. So there are two ways of doing that, and this is tantamount to kicking the swing. What happens next? C is the degree to which you kick it, and T0 is the time when you apply the kick. Alright, so how would something like this be solved? First of all, we use the method of Laplace transforms. So applying the Laplace transform to both sides, I get Laplace transform of y double dot plus omega squared times the Laplace transform of y is equal to the constant c times the Laplace transform of delta t minus t naught. Now here I'm going to follow the engineering folks and come up with the notation for writing the Laplace transform of y. The Laplace transform of y in engineering is usually called y of s, or simply capital Y. Let me assume that some initial conditions are given. So let me call C1 the value of y at 0 and C2 the derivative of y at 0. Because we need the initial conditions to isolate the Laplace transform of the second derivative. From the previous video, we know that the Laplace transform of the second derivative is going to be s squared times the Laplace transform of y itself, which I've indicated as capital Y, minus s times the first initial condition minus the second initial condition. So it's a descending series, descending polynomial, plus omega squared capital Y equals the Laplace transform of the delta function t minus t naught. Well, here all we have to do is evaluate the actual thing. The Laplace transform of a function, any function, is the integral from 0 to infinity. That function times e to the minus st dt. Now by the extraction axiom of Dirac delta functions, this is just c times the value of the function, because this is like your function f of t in the previous video where I showed you what the Dirac delta function does. It extracts the value at the place where the extraction is carried out. Here the extraction is carried out at t0. To find the place where the extraction is carried out, set the argument of the delta function to be 0, so I get t equals t0. And so this gives me e to the minus st0. Done. Now all I have to do is solve for capital Y. Now in order to do that, I combine all the terms involving capital Y and move to the right side things that do not involve capital Y. So far it's looking really nice, and I have capital Y equals C1 times S over S squared plus omega squared plus C2 divided by S squared plus omega squared plus C divided by s squared plus omega squared e to the minus st0. Now we are in trouble. How are we going to write this as a Laplace transform of something? There's a useful lemma which I will state shortly that will help us there. Meanwhile, let's try to figure out what these are Laplace transforms of. Simply consulting a table will tell you that the Laplace transform of cosine omega t is s over s squared plus omega squared, and the Laplace transform of sine omega t is omega over s squared plus omega squared. Omega here is a constant. So we know that that should be cosine and that should be sine, and that's something we don't know yet. Let's proceed. So this is going to be C1 times the Laplace transform of cosine omega t. Now to get omega, I can multiply and divide by omega. So I get C2 over omega Laplace transform of sine omega t plus something we don't know. Now here I would like to introduce a lemma called the translation lemma. To state the translation lemma, let's first talk about a function that's like the Oliver-Heaviside function but at a different value. That is sometimes called a c-step function. So the c-step function is just the translated Heaviside function. I introduced the Heaviside function in the previous video. You translate the Heaviside function by the argument c. So the graph of if c is positive, the graph of the translated Heaviside function or the c-step function would look like this. The definition is exactly the same. It is 0 for t less than c. This is the time you come to the room and switch the on-off switch at time t equals c. And it is 1 if t is bigger than c. So the two translation lemmas we need are the following. If we call f of s the Laplace transform of f of t, or I could have called it y, but I don't want to confuse it with the y here, then the Laplace transform of the c-step function times the function at t minus c is equal to e to the minus cs f of s. You can see how that immediately applies to something like this. The second lemma is the Laplace transform of, it's like the yin and the yang. If you multiply the function with the c-step function, then you get e to the minus cs fx. But what if you multiply the function with e to the ct instead? Then you get the function translated, the Laplace transform translated by c. Both these lemmas are very easy to prove. It's just following the definition, and it's done in the notes. I will assume these lemmas to be given to us, and we can use these lemmas to solve the problem of impulsively kicking a swing with your enemy on the swing. So that's the translation lemma 1 is what we need to use. Applying it, I'm going to get, this is going to be, so step star y is going to be c1 times the Laplace transform of cosine omega t plus c2 over omega, the Laplace transform of sine omega t, plus I'll write this as the Laplace transform of uc, c in this case is t naught, f is everything else. Now the Laplace transform of c over s squared plus omega squared is sine related, so it's c over omega sine omega t minus t naught. Okay, now you have Laplace multiplying everything. step function only activates itself at t0. So to find y, which is the inverse Laplace transform of y, all I have to do is remove the L's, capital L's, from all of this. So I'll just get c1 cosine omega t plus c2 over omega sine omega t plus ut0 of t. I can write c over omega first. C over omega ut0 of t sine of omega t minus t0. Remember, omega and t minus t0 occur together because the dimensions of omega is radians per second and the dimensions of t is seconds, and sine can only be fed radians or it'll get a stomach ache. Now that we have the function, we can write the function in a two-step process because people may not recognize what this is. So the full solution to the problem is, before you kicked your cousin, well, I don't know where the cousin came from, but before you kicked the swing, so c1 cosine omega t plus c2 over omega sine omega t for t less than t0, because before t0, the c is equal to t0 here, the swing was not disturbed. Then you came and kicked it. So after t0, you have the same behaviors that you had before t0, because the swing still remembers the simple harmonic aspects of the motion. As you may have guessed, this part is just going to be simple harmonic with sines and cosines, and this part is going to be the delta kick. And then because you kicked it, there's going to be a potential resonance. So the swing amplitude may go up in a tremendous way and the person could be thrown off. And that is the full solution to this problem with delta forcing.